All right, let's just jump right in. Inside your head, right now, is one of the most complex things in the entire universe. It's a living, breathing network of connections so dense that if you could somehow lay it all out end to end, it would stretch for 100,000 miles. It's the wiring that makes you, well, you. But how in the world do you even start to map something like that?
So that's the big question, right? That's the challenge that neuroscientists are up against every single day. If we want to understand literally anything about the brain, from how we learn new things to what's going wrong in diseases, we absolutely need a reliable map of this incredible circuitry.
Now, these connections aren't just a jumbled mess of wires. Think of them more like the brain's information superhighways. They're these huge, organized bundles of nerve fibers, technically called white matter tracts. And their job is to act like high-speed data cables, zipping signals between different parts of the brain so that you can think, feel, and act all at once.
Okay, but here's the kicker. Just like the layout of roads is different in your town than it is in mine, the exact 3D map of these neural highways is unique to every single person. And this variability, this difference from person to person, has been a massive roadblock for science. It makes comparing brains across different people incredibly, incredibly difficult.
So what do? How do you compare a bunch of maps that are all slightly different? Well, what you need is something like a personalized GPS for every single brain. And that right there is where a method called tractometry comes into the picture.
And tractometry is it's a brilliant way to solve this problem. See, instead of trying to squish every brain scan into some kind of one-size-fits-all map, it does the opposite. It starts by identifying the main superhighways in your specific brain. Then it uses those highways as a unique personalized coordinate system. It finally allows for a true apples-to-apples comparison across lots of different people.
So, tractometry is the big idea. But how do you actually put it into practice? Reliably and on a huge scale? Well, one of the most powerful ways to do it is with a process called automated fiber quantification, or just AFQ for short. AFQ is really elegant. It works in three main steps. First, software generates millions of potential pathways through the brain, kind of like sending out scouts to explore every possible road. Then, and this part is absolutely crucial, it filters all those possibilities using known anatomical landmarks. It's like checking a real map to make sure a highway actually connects two cities. This is what guarantees accuracy. And finally, for each real highway it finds, it measures the physical properties all along its length, creating this rich data set called a tract profile.
But a powerful method is only really useful if scientists can, actually use it. And this is where the story gets really, really cool. Because it's not just about one new tool. It's about an entire ecosystem of tools. A whole new Swiss Army knife for neuroscientists. You have to understand, in the past, doing this kind of analysis was just a huge pain. It was incredibly slow, you had to piece together all these different bits of software, and honestly, you pretty much needed a PhD in computer science on top of your neuroscience degree just to make it all work. But now, that's all changed. Researchers have built this fully integrated open-source software ecosystem that handles the whole shebang, from start to finish. It's a total game changer, taking this powerful technique out of a few specialist labs and putting it into the hands of scientists all over the world.
This ecosystem has four main players that all work together. You've got PyFQ, which is the workhorse, the core engine doing all the heavy lifting. Then there's AFQ Insight, which is like the data scientist in the box, bringing in machine learning. Tractable handles really sophisticated stats, and AFQ Browser lets you see and explore your results with these amazing interactive visuals.
So what does all this actually mean for brain research? What does having this toolkit actually unlock? Well, in a word, everything. We're talking about faster processing and much, much deeper insights.
Let's just talk about speed for a second. Processing the data for just one single person used to take hours of computer time. Hours. With this new ecosystem, that same exact analysis is done in minutes.
And get this, if you have access to modern graphics cards, GPUs, the speed up is it's staggering. We're talking about a 60 times acceleration for the most time-consuming step. That's not a small tweak. That's the difference between a research study taking months versus just a few days. It is a massive leap forward.
Now you might be thinking, okay, it's fast, but is it sloppy? And the answer is a huge no. In fact, it's more accurate. The secret sauce in the AFQ approach is using those anatomical constraints we talked about, basically telling the software where a pathway should start, where it should end, and just as important, where it definitely shouldn't go. That's what makes the results both super fast and super reliable.
And all this efficiency isn't just about making life easier for scientists. It fundamentally changes the kind of questions they can even ask. With processing times totally slashed, researchers can now use really complex, data-hungry machine learning models to find patterns that were completely invisible before.
For instance, check this out. Researchers took data from over 1,800 people and trained algorithms to predict someone's age just by looking at their brain wiring. A standard model did pretty well, getting an accuracy score of 0.62, but an advanced neural network, which can see more complex relationships, did even better. This is exactly the kind of deeper insight this new toolkit makes possible.
So, when you put it all together, what you have isn't just a simple software upgrade. It's a whole new paradigm for how we study the brain. And it's all built on the amazing idea of open science.
The real-world applications are just wow. Scientists are already using these tools to do incredible things. We're talking about tracking exactly how our brain's wiring develops as we grow up, finding the very earliest signs of terrible diseases like ALS, understanding how aging affects our brain connections, and even watching in near real time how learning a new skill physically reshapes the brain.
And maybe the most powerful part of this entire story is that this whole ecosystem is completely free and open source. That means any scientist, anywhere on the planet, can download it, use it, and even build on top of it. It just breaks down all the barriers and puts the pedals to the metal on the pace of discovery for everybody.
So we have the tools. They're faster, they're more accurate, and they're more accessible than anything we've had before. This is a massive leap forward in our ability to finally map and understand those information superhighways in our heads. Which really just leaves us with one final, very exciting question. Which mysteries of the brain will we solve next?